We have seen the different concepts of acids and bases, and also we have classified, based on these concepts, we have classified different compounds into acids and bases. And we have also seen that among the acids there are strong acid, weak acid, strong base, weak base, depending upon the ability of it to ionize or to give away proton or accept the proton, give away hydroxyl ions, etc., etc. We'll see. We have defined everything in detail in the last video. Now here in this video we'll be discussing about the factors which influence the strength of an acid or a base. Now, there are various factors which influence or affect the strength of an acid and a base. Now, few factors which are affecting the strength are the solvent in which the acid or base is present, the nature of the substituent on the acid or base, particularly if in organic case, organic acids, this is very important, acids and base, this is very important. Then we have to discuss the P-pi back bonding is another factor. This is particularly related to the Lewis acid and base, acids and bases. Then electronegativity of the element present in central atom present, and the charge density on it, then the hydration energy, the way the acid and base is hydrated, and the resonance effect. This again, resonance effect again is more pronounced in organic acids and bases. Now we'll see individually each factor in brief. Let us take up the first one, the solvent. Now in the case of solvent, the proton accepting and donating nature of the solvent and the polarity and dielectric constant of the solvent decides the strength of acid and base. Now in the proton accepting and donating nature of the solvent, let us take the first one, an example, nitric acid, acetic acid. Now acetic acid is a solvent, nitric acid is the acid in it. Now we know that in aqueous media, nitric acid is very strong. It ionizes readily, it gives away the proton readily. Now in this case, we have nitric acid, we have acetic acid. Now here, HNO3, nitric acid is the proton donor, so it is the acid, and acetic acid accepts the proton, so it is the base. So you have the acid, acetic acid the base, the solvent, acetic acid the solvent. Then you have the corresponding conjugate acid and conjugate base. Now here HNO3 acts as a weak acid because the acetic acid does not have a great tendency to accept the released proton. So the proton releasing capacity of HNO3 is brought down. Thus it acts as a weak acid. But in the case of water, in the presence of water, HNO3 is a very strong base. It readily gives off its H plus ion, right? Here nitric acid, HNO3 will be the acid and water will act as the base, and H3O plus is the corresponding conjugate acid for H2O, and NO3 minus is the conjugate base for HNO3. So here the H2O readily accepts the proton, and hence HNO3 readily gives off its proton, and thus it is a strong acid. Now in HF, when the solvent is HF, hydrogen fluoride, HNO3 doesn't show its acidic property as such. Though HNO3 is considered to be the acid and HF as a base, you can see the corresponding acid. It is the HF gives off its proton actually, so it's working in the other way around. Though we expect the HNO3 to be acid and to be the donor of proton, it is HF that is donating the proton. Okay, so the HNO3 is in fact forced to act as a weak base here. Alright, because it is accepting the proton released by HF. So HF is the acid here actually, and HNO3 is the base here. Okay, though we expect HNO3, and we are considering HNO3 as an acid in all these cases. But here, in the presence of HF, HNO3 is forced to behave as a base. Now, but when you take acetic acid and HF, In the presence of water, acetic acid acts as a weak acid, right? We know that. Now, in the presence of HF, acetic acid will act as a base. HF will release its proton, and acetic acid will accept the proton, and thus acetic acid acts as the base, and HF will be the acid. So acetic acid here in the presence of HF acts as a strong base. Now, the same acetic acid in the presence of ammonia acts as a strong acid. Now here, when ammonia is a solvent, what happens? Ammonia is a strong base. It will abstract the proton from acetic acid. So acetic acid releases its proton easily. So acetic acid acts as a strong acid in the presence of ammonia. Alright, and ammonia becomes ammonium ion, and acetic acid becomes acetate ion. Okay, so that's because of the strong basic character of the ammonia. So depending upon the nature of the solvent, that is depending on the proton accepting and donating nature, what does that mean? It's the basic or acidic nature of the solvent, the strength of the acid varies. Now this can be explained in terms of leveling solvents and differentiating solvents. Now what is leveling solvent and differentiating solvent? Solvent whose proton accepting or proton donating tendency is such that different acids or bases are ionized to the same extent is called leveling solvent, and that effect is called a leveling effect of the solvent. That means in a particular solvent, if all the acids show or all the base show the same strength, then we call that solvent as a leveling solvent, and that effect as a leveling effect. Now say for example, HClO4, H2SO4, HNO3 and HCl have the same strength in water. Okay, regardless of the nature of the acid, all of them have the same strength. And thus we can say that water is the leveling solvent of these acids. Okay, now this leveling effect can be explained in terms of solvent system concept of acids and bases. Now what is this solvent system concept? Now the strength of all acids stronger than the characteristic cation of the solvent would be leveled to that of the cation of the solvent. What does that mean? That means you have a solvent, it has got an anion and a cation. And suppose if the strength of the acid is higher than that of the cation of the solvent, their strength will be leveled to that of the cation. All the strength of all those acids will be brought in par with the strength of the cation. Alright, that means what does that indicate in these cases? HClO4, H2SO4, HNO3 and HCl. Now these acids have a strength greater than H3O plus, the cation of the solvent, or H plus of the solvent, cation of the solvent, H3O plus, that is water. So the strength of all these acids are brought to the level of H plus ion or H3O plus of the solvent. Now that is called the solvent system concept. That's how the solvent levels the strength of all acids in the same way. That means all acids will be having the same strength in that solvent when the strength of the acid is greater than the strength of the corresponding cation in the solvent. That is solvent system concept, and that explains the leveling effect or leveling solvents. Similarly, in the base. In the case of base, if the strength of the base is greater than that of the anion of the solvent, then the base will be leveled, the strength of all the base will be leveled to that of the anion of the solvent. So if you take NaOH, the base, the strength of the NaOH is brought to the level of the OH minus of the solvent. Alright. Now what is differentiating? So here you have the example here. Acetic acid and OH minus ion. You get acetate ion in water. So OH minus ion is the base, acetic acid is the acid, acetate ion is the base, and H2O will act as the corresponding conjugate acid of the base. Alright, now here in this case, the hydroxide ion, the strength of acetic acid is leveled. Now here you have aniline and acetic acid. It gives an acetate ion and anilinium ion, C6H5 NH3 plus. Now what's happening here? Here sodium hydroxide, which gives off OH minus ion, and aniline, okay, in the presence of acetic acid, what's happening? These two have the same strength when acetic acid is the solvent, okay, because their strength is leveled to that of the acetate ion. The strength of NaOH and the strength of aniline is leveled to that of the acetate ion. Now what is differentiating solvent? A solvent whose proton accepting or proton donating tendency is such that different acids ionize differently in different extent. Okay, so that we can differentiate the strength of the acids. Then it is called the differentiating solvent. Now, a differentiating solvent for acid will be having cation stronger than the acid. Okay, so its strength can be compared to that of the acid. And in the case of base, the anion will be stronger than that of the base. Now here if you have HA and acetic acid, okay, you have acetic acid takes up the proton and A minus is formed. So acetic acid acts as the base here. Okay, so it's differentiating here. Now, in the case here, you have HClO4, HBr, H2SO4, HCl, and HNO3. I have arranged them according to the decreasing order of their acid strength. This is in presence of acetic acid. So here, acetic acid differentiates the acid according to their acidity. Now, why is that so? It is because the cation, the acids and bases ionize in different extent. Okay, it is because the cation of the acid is stronger than the strength of the acid. Okay, and thus you have these acids will show their different strength in acetic acid. So acetic acid is a differentiating solvent for these acids. Alright, now coming to the next factor, that is polarity and dielectric constant of the solvent. Now greater the polarity, greater will be the dielectric constant of the solvent, and thus greater will be the extent to which the force of attraction between the ions of the solute is decreased and the strength of the acid and base will be decreased. So if the solvent is highly polar or having high dielectric constant, the ionization will be decreased and thus the strength of the acid or base will be decreased. So in polar solvent or solvent having high dielectric constant, the strength of the acid and base will be decreased. The next factor which decides the strength of the acid and base is the nature of the substituent. This is particularly for organic acids and bases. Now, the electron withdrawing or donating nature of the acids and the nature of the substituent decides the strength of acid and base. Now, for example, in the case of organic acids, presence of an electron withdrawing substituent will increase the strength of the acid, and presence of an electron donating substituent will decrease the strength of the organic acid. Now, for example, we have chloroacetic acid and acetic acid. The chloroacetic acid is stronger than acetic acid. It's because the presence of chlorine group in chloroacetic acid the chlorine group is an electron withdrawing group. So it will withdraw the electrons, and therefore the protons on the COOH will be easily released. So the acidity of chloroacetic acid increases when compared to the acidity of acetic acid, because there is no electron withdrawing group attached to the acid. Alright, now in the case of bases, electron withdrawing substituent will decrease the strength of the base, and electron donating substituent will increase the strength of the base, particularly organic base. Now, for example, we have methylamine and ammonia. Now, in the case of methylamine is stronger than ammonia. Now, the reason is both ammonia and methylamine has an electron pair on the nitrogen. Now, the methyl group is an electron donating group. So, it will increase the electron density on the nitrogen of methylamine. Therefore, the strength of the electron donating, or the electron's density on nitrogen will increase. Thereby, the basicity of methylamine will be more when compared to that of ammonia. Now, if there is an electron withdrawing group, what will happen? It will withdraw withdraw the electron or draw the electrons towards itself. Thereby, the electron density on nitrogen will decrease. The strength of the acid will decrease. Alright, so this is how the strength of acid and base is decided by the nature of the substituent. Another factor is the steric effect of the substituent, the steric factor. That's another factor, or another property of the substituent which decides the strength of the acid and base. Now, if we have trimethylamine and dimethylamine, you take these. In these two cases, you have got electron donating substituents. So, the strength of the amino group will be increased by, since here you can see, there are three methyl groups. So, actually we expect methylamine to be more stronger than dimethylamine. But trimethylamine, the basicity of trimethylamine is found to be less than the basicity of dimethylamine. Now, the reason is the three methyl groups attached to the nitrogen will sterically hinder the approach of the cation, alright, or the electrophile. So, even though there is an electron donating group on the nitrogen, the basicity is lowered because of the steric hindrance. It inhibits the approach of the acid towards trimethylamine. Okay, so that's why trimethylamine is less basic than dimethylamine. So, these are the factors related to the substituent on the acid. Now, another factor which decides the strength of acid and base is p-pi back bonding. Now, in the case of BF3, BBr3 and BCl3, the the acidic strength is in this order. That is, BF3 is found to be less acidic than BCl3 or BBr3. Even though we expect BF3 to be more acidic as it is highly attached to more electronegative fluorine atoms. The boron is attached to more electronegative fluorine atom. So we expect BF3 to be more acidic. But contrarily, or than what has been expected, BF3 is the least acidic among these three. Now, this is because in the case of BF3, there is a shift of electron density from fluorine to bromine. There will be a shift of electron density from fluorine to bromine via pi overlap between the vacant p orbital of boron and filled p orbital of fluorine. So, this is called p-pi back bonding. Okay, so there will be an electron shift, electron density shift from the vacant p orbital of between the vacant p orbital of boron and filled p orbital of fluorine. So because of this p-pi back bonding, the electron accepting power of boron is reduced, and boron becomes an electron deficient center and its acidity decreases. Okay, now this back bonding, p-pi back bonding is not observed in BCl3 or BBr3, but it is observed in BF3. Now that's why BF3 is least acidic when compared to the rest. Okay, so in BF3 there is a shift of electron density from fluorine to boron through a pi overlap between the vacant p orbital of boron and filled p orbital of fluorine. Okay, this decreases the electron accepting power of the electron deficient center boron. Thus the boron, this is not found in other boron halides but only in BF3. Alright, now the next factor is electronegativity of the atom in the acid. Now if we take the hydrides of the nitrogen, oxygen and fluorine, the acid strength is in this way. That is, HF is more acidic than H2O, which is more acidic than ammonia. Ammonia is the least acidic. So this can be explained on the basis of the electronegativity of nitrogen, oxygen and fluorine. Fluorine is the most electronegative atom. So the proton will be released easily when it is attached to fluorine. Okay, now the charge density also decides the strength of acid and base. Now when you take the halides, hydrogen halides, HF is least acidic and HI is most acidic. Okay, and that is because of the variation in the charge density. Here the charge density outweighs the electronegativity effect. When the charge density is lower, the proton will be loosely held and it will be easily released. So in HI the charge density is lower. So ionization is greater when the charge density is lower. So HI is more acidic. Another factor is the hydration energy. Alright, now in the case of this one, more negative the hydration energy value, this will favor ionization better. So here the HI is having highly negative, more negative hydration energy value. Okay, and that's why HI gets ionized easily. So for halogen acids, the enthalpy of ionization is more negative for HI and the least for HF. Hence the tendency for ionization and acid strength is more for HI and least for HF. So this is the order of acid strength of all the halogen acids. Now coming to the next factor, that is resonance effect. This is basically seen in case of organic acids. Now let us take phenol as an example. Now phenol exists in all these 5 resonance structures. So phenol is a combination or has got all these 5 resonance structures. Now here you can see that there is electron delocalization of the oxygen lone pair over the aromatic ring. The electron on the oxygen lone pair is delocalized over the aromatic ring and a positive charge appears on the oxygen. For presence of this positive charge on the oxygen will help in the release of proton, and thus phenol is highly acidic. Moreover, when a proton is released, phenoxide ion is formed, and phenoxide ion is resonance stabilized by these 5 resonance structures. So you can see here the negative ion charge on the oxygen also take part in the resonance, or also becomes a part of the, or you can say is delocalized in the aromatic ring. Okay, so the delocalization of the lone pair of electron on oxygen in the phenol results in the formation of a positive charge on the oxygen, thereby the proton is on the phenol is easily released. And when the proton is released, a phenoxide ion is formed, which is resonance stabilized. So this will increase the acidity of phenol. But alcohols do not show, that is aliphatic alcohols do not show such acidity because there is no resonance stabilization. Phenols are highly acidic. Now, the substituent on this aromatic ring of phenol also decides the acid strength. Now, when the groups like electron withdrawing groups like nitrate, NO2 or CHO group are present, or when electron donating group like OH or OCH3 are present, that will influence the strength of the acid strength of the phenol, and also the carboxylic acid, and also the basic strength of amines. Alright, that we have already discussed in the nature of substituents. So these are the factors which affects the strength of acids and bases. Thank you.